A language model gives you an answer. An agent gets to see what happened and decide what to do next. ReAct packaged that difference into 3 repeating beats: thought, action, observation. Watch one complete loop. The model writes a thought, sends a search action across the boundary, and receives front row as evidence. That observation is appended to the live context. Now the next thought is different because it can read that evidence. It reformulates the query, acts again, and extracts keyboard function keys instead of repeating an unsupported guess. ReAct did not invent agents, tools, or feedback control. Its durable move was narrower, put generated reasoning and environment interaction into one readable, evolving transcript. Before ReAct, consider the 2 incomplete halves. Reason only can decompose a problem, but without an external observation channel, an invented fact has nowhere to be corrected. The paper's chain of thought example silently swaps front row for Apple TV. The false edge turns red, then every downstream conclusion inherits the error. Act only has the opposite problem. Commands can touch the world, but without explicit language space planning or working memory, the path can repeat and fail to synthesize an answer. ReAct joins the missing edges. Reasoning chooses and tracks actions, observations ground and revise later reasoning. The work appeared in 2022 and was published at ICLR 2023. Formally, the agent sees a context tape, observations and actions accumulated through time. A policy selects the next move from that entire trajectory, not from the original question alone. The key move is tiny. The ordinary action set A becomes A hat equals a union L, where L is the space of free-form language. A thought from L does not cross the environment boundary. It changes the transcript by recording a plan, fact, checkpoint, or exception, but it does not itself change the world. A task action does cross that boundary. The tool or environment returns an observation, which expands the context. The next computation can now depend on what actually happened. On knowledge tasks, the paper alternated thoughts, actions, and observations densely. In long interactive tasks, thoughts appeared sparsely and asynchronously, mainly when the plan needed a checkpoint. The paper's clearest knowledge example asks, aside from the Apple Remote, what other device can control the program it was originally designed to interact with? Reason only asserts that the remote was designed for Apple TV, then concludes iPhone, iPad, and iPod Touch. The first link was never retrieved, so the whole answer rests on red. Act only does retrieve. Search Apple Remote returns the front row Media Center program. Search front row then misses the exact page and offers similarly named entities. It even reaches front row software. But without an explicit synthesis step, it finishes with the word yes. Useful observations alone do not guarantee a useful answer. Rewind the same machine. ReAct first writes the subgoal, find the program Apple Remote originally controlled. Then it issues search Apple Remote. The returned sentence identifies front row. Only that evidence span is lifted into the context tape, and the next thought converts it into a new search target. Search front row fails. That is still an observation, not a dead end. The suggestions expose a disambiguated entity, front row software. The next thought reads the failure and reformulates. Search front row software now reaches the intended page instead of blindly retrying the same command. The description says front row can be controlled by an Apple Remote or keyboard function keys. ReAct extracts the second device and finishes keyboard function keys. Observations need not be prose from a browser. In one ALFWorld trajectory, the task is to put a clean knife on a countertop inside a text-simulated home. A thought decomposes the job into a state register: find and take the knife, go to the sink, clean it, then place it on the countertop. The agent checks cabinets, drawers, and countertops. Several actions occur without a new thought. Each visited location reveals only its local objects while the plan stays stable. At countertop 2, the observation reveals knife 1. A sparse checkpoint records knife found, and taking it advances the register from find to hold. The next checkpoint selects sink basin 1. After navigation, the clean action changes the object token itself. The held knife becomes a clean knife. The agent returns to countertop 1 and places the clean knife. The final environment observation, not the model's confidence, marks the trajectory successful. In the same game, Act only tries to clean from the countertop before going to the sink. The environment says nothing happens and the path cycles through impossible commands. Now the numbers, with metrics kept separate. On Hapaka exact match, raw ReAct scored 27.4. Raw chain of thought scored 29.4. ReAct did not win this comparison. On fever accuracy, chain of thought scored 56.3, Act only 58.9, and ReAct 60.9. Here external retrieval helped raw ReAct lead both controlled baselines. The strongest prompting results were hybrids. ReAct backing off to self-consistent chain of thought reached 35.1 on Hapuka, the reverse fallback reached 64.6 on Fever. On ALFWorld, ReAct averaged 57% across 6 prompt trials and reached 71 best of 6. AC's best was 4 to 5, Butler's best was 37. 71 minus 37 is 34 points. On webshop success rate, ReAct reached 40.0 versus ACT only at 30.1, a 9.9 point gain, roughly 10. Human experts reached 59.6, far above both. So the empirical story is specific. ReAct beat ACT only across these tests, beat raw chain of thought on Fever but not Hapuka, and remained well below stronger references or humans. A loop can amplify mistakes too. A bad thought selects a bad query, an empty observation returns, the next thought copies the mistake, repetition tightens into a failure spiral. In a manually labeled hotpot sample, 47% of ReAct failure cases were reasoning errors and 23% search result errors. Those are conditional failure labels, not population-wide rates. The main system was a frozen palm 540 billion prompted with human-written trajectories, 6 examples for Hapuka, 3 for Fever, and only 1 or 2 in the interactive tasks. Its Wikipedia tool exposed only search, string lookup, and finish with exact title sensitivity. Observations can be empty, noisy, stale, or misleading. ReAct does not manufacture a good retriever. Generated thoughts make a trajectory easier to inspect and edit. They are not guaranteed to be a faithful readout of hidden computation, and the paper itself shows erroneous visible traces. The benchmarks constrained actions, no real purchases or Wikipedia edits. Broader tools can leak data or cause harm. Palm was not openly accessible, and large action spaces can exceed context limits. Historically, the cradle metaphor needs care. WebEE already browsed, Saken selected robot actions, inner monologue supplied environmental feedback, and the ReAct paper explicitly says it built on that closed-loop work. Later agent systems wrapped the recognizable loop with structured tool calls, planners, persistent memory, reflection, verification, permissions, sandboxes, and multi-agent orchestration. Those modules were not in original ReAct. Not every later agent descends directly from this paper. But ReAct gave the LLM-era a compact interface where reasoning and action share one closed-loop transcript, a cradle, not the whole family tree. The center remains recognizable. Compute a next step. Act. Read the result. Update state. Repeat. ReAct was not the whole agent, it was a loop a much larger agent stack could grow around.